Hi, we're in section 4.5. You just learned about expected value, and that's the mean of a random variable. And 4.5 is mostly about the variance, which is the amount of spread a random variable has about its mean. And the point is, expected value alone can tell you again what the average, but it's nice to know how much variation, or well, we just say spread about a random variable there is. So this problem, I like this problem. It's a real situation. The graphs and all that might not make sense, but the whole reason I talked about it was to bring up a point that different graphs have different variances. And the reason I had, well, I'll just explain this one fast because it is kind of cool. The German tank problem, this is also a pretty famous problem. Um, what happened during World War II is the Germans had a bunch of tanks, and we would capture a tank and try to then determine how many total tanks the Germans had. And the reason we were able to do this or estimate this is because they had sequentially ordered the numbers of the tanks. So they may not have started with one, but they were a nice, like, 2, 3, 4, 5, 6. So we would capture so many tanks, and from those numbers try to estimate what the maximum number of tanks it was that they would have. So as an example, in class I said, imagine like these are five numbers. You just caught five tanks, and this is a sample of five numbers from that distribution. Could you then estimate the maximum number of tanks they have totally? And actually, this isn't a good, I shouldn't have used a sample. The graphs below show, I've done this example in class where I put a bunch of numbers in a bag and people pick out five, and I've had the maximum number in the bag be, as you can see here, 312. And I have the class come up with different ways they might estimate what the maximum is based on these five numbers. But you can see 317 doesn't make sense if, yeah, that couldn't be possible if the max was 312. But imagine again you have five numbers. How would you estimate a maximum? One thing you could do is just take the max of your sample and hope that that's close to the maximum of your population. And so I did a bunch of simulations with, again, if the max was 312, and took a random sample of five, and every time took the max of that. And you can see, you get a graph that always will underestimate what the true maximum is. A lot of ideas that people give to estimate what the max is: take the min plus the max value from your sample. So probably the max isn't enough, and add a little bit on to get the min. And you can see when I did simulations with that, you get pretty nice distribution about the truth, which is 312. Here's another way. You take the mean of your five numbers multiplied by 2. You take the median of your five numbers multiplied by 2. So these are all simulations. The point why I did this problem is just to show what I mean by variance. Variance is just the amount of spread there is in a random variable, how much spread there is about the mean. So notice if the mean here is 312, pretty much most of your days within 210 to 420, but here's 210 to 420 here. So this is again another estimator, but you see you have more variance here and even here. So in just doing simulations right now, the one that looks pretty nice is actually just the min plus the max. But so I need some definition of variance. I wanted some way to measure spread. So variance is a measure of the amount of fluctuation about a random variable from its mean. And how are we going to do that? So one way we could do is to say, how far are the x's away from what we expect x to be? Like, how much difference is there between these x's and the expected value of x? And take the expected value of that. But the problem is, expected value of x minus mu, if you use the rules we did on expected value, that's just expected value minus expected value of mu, which is mu minus mu, which is 0. So notice, if your estimate of variance is you just are taking the distance from mu on both sides, they're going to cancel each other out and you're just going to get 0. So that's not a good measure. Another measure would be to take the absolute value. So in absolute value, how far is the x's away from mu? The expected value of that. And so I'm just using law of unconscious statistician again. But the problem, this isn't a bad definition, but who really, really wants to work with absolute value? So this might be a nice way to describe spread, but it just, imagine later we're going to be taking derivatives and stuff. You don't want to really work with the absolute value of x minus mu. So I still want the idea that when I take positive and negative numbers here, that they don't cancel out and give me 0. So absolute value is a good idea. So instead of going absolute value, the way we define variance is we use a square. So we're going to say x minus mu squared. So the definition of variance is expected value of x minus mu squared. How far are your x's away from mu in general, on average, and square that so I don't get it to be 0. Standard deviation, square root that thing. And so again, I told you this would be so popular. Law of unconscious statistician says expected value of x minus mu squared is p of x times x minus mu squared. So that is my definition for variance. And here's an example, just an interesting fact. Here's an example with rolling a die. So you can see the definition, p of x times x minus mu squared, p of 2, 2 minus mu squared, p of 3, 3 minus mu squared. Okay. What's very nice is there's a shortcut formula. I often don't use this to compute variance. There's something a little bit nicer. If you multiply out that expression, this is a nicer way to compute variance. This would just require law of unconscious statistician, and this is just your mean squared. So down here I did a short proof of how I got from variance of x using the old definition, or the definition we started with, to get this very, very nice way to define variance. So notice I just did a few examples here. Using the die example, that's expected value of x squared minus expected value of x squared. This is law of unconscious statistician. This is mu squared. Very nice. Same way down here. Just another example. Okay, let's go a little bit further down. There's other theorems about variance. The variance of a constant function is 0. If your function's constant, there's no variance. This is another nice theorem. Why, if you have a constant in front of your random variable, why that constant comes out front of your variance squared. I thought I would leave that as a bonus. So just start with this side and the definition of variance, and you'll work through and you'll eventually get down to this. So if you want this as a bonus, I have it for tomorrow night if you wish to submit it. You really just start with what the definition of variance is and kind of work through, and eventually you'll get everything canceled very nice and you'll see that. So it's not hard, it's kind of it's a fun little proof. Do I have anything else here? Oh, just a few more examples of, again, because of what we just said about variance, if I want the variance of 2x plus 1, that constant's going to come out front squared, so it's 4 times the variance of x, and then the variance of 1 is 0. So just a few more examples. Expected value variance, expected value variance. The last thing, we're not going to go, another nice theorem, I think that's pretty nice, but moments, we're not going to use these till we get to chapter 11, moment generating functions, but we call the expected value of x to the k the kth moment of a distribution. So expected value of x to the first is your first moment. We know that's the mean. Expected value of x squared, that's the second moment. This is the nth moment. So we have moments, and later we'll use moments. For example, we use the first 2 moments to define variance. I think it's the first 3 to find skewness, kurtosis, etc. So moments are useful for finding different aspects of a random variable. Spread, well, we already know spread, but peakedness, tails, long tails, etc. So, okay, that's it for chapter 4.